Okay, what we're going to do now is a planetary mechanics problem. I'm going to do a problem that has gravity in it and centripetal force. This is a very common type of problem because you can get, there's so many variables in here that I can come up with many, many problems. So what we want to do is find the period of a satellite at an altitude of 200 kilometers. I got to notice the word altitude here because in all our formulas we're dealing with the distance from the center of one object to the center of the other object. But the number I'm given is the altitude, which is 200 kilometers, is the distance from the surface to the satellite. So I'm going to have to add the radius of the Earth to get this number that I need, r. I'm given a bunch of variables, the radius of the Earth, the mass of the Earth, and g. And I have two formulas I can work with. The gravity formula that tells the attraction between two objects, and our centripetal force formula. Any object going in a circle, this formula governs its motion. Any two objects that are attracted to each other, this governs the attraction. And what we can notice about it is, if an object is orbiting, like this satellite orbiting the Earth, there's gravity between them. There's gravity between the Earth and the satellite. That's the gravity that's holding it in orbit, and that's the formula that calculates that gravity. But because this object is going in a circle around the Earth, then it must follow the laws of centripetal motion, which is this formula. Meaning the amount of force on it must add up to these variables. So the gravity on this is supplying the centripetal force. So what we can say is the gravity on the object, the attraction between the two objects, is equal to the centripetal force. This is always the case. As a result, look at all these variables here. There are many, many questions we can come up with. The one we're looking at today is finding the period. We're looking for this number. Okay? Now, in this formula, I have both masses, the mass of the Earth, the mass of the satellite. In this formula, I have another mass. This mass here is the mass of the satellite, because with the centripetal force formula, the mass you plug in is the mass of the object doing the rotating. So I can cancel out that mass. That's the mass of the satellite, which tells me it doesn't matter what the mass of the satellite is. Any satellite you put in that orbit under these conditions will do what this satellite is doing. So I have my two formulas. I set gravity equal to centripetal force. I get rid of the mass of the satellite, so this is the mass of the Earth. So I end up with g times the mass of the Earth divided by the radius of orbit of the Earth squared is equal to 4 pi squared radius of orbit divided by period squared. Now this radius is the radius of orbit, the distance between the center of the Earth and the satellite. It appears in both formulas. It doesn't cancel out at all, because this is in the denominator. What's going to happen is when I rearrange it, this is going to get together with that, and we're going to have r cubed. So I got to rearrange this to solve for the period, and if I do that, I get the period squared is equal to 4 pi squared r cubed over g times the mass of the Earth. So all I did was rearrange it. I multiplied both sides by period squared, that's how I got that over there, and then I rearranged the rest of them and end up with that. All I have to do at this point is plug in numbers. But I need this r, radius of orbit. The radius of orbit is how far the satellite is from the center of the Earth, which is going to be the radius of the Earth plus the altitude, this height, which is 200,000 kilometers, which is 200 kilometers, which is 200,000 meters. So I get radius of the Earth is 6.38 times 10 to the 6 plus 2 times 10 to the 5. So I get 6.58 times 10 to the 6 meters. That's r. So now I can plug all my numbers in here. T squared equals 4 pi squared 6.58 times 10 to the 6 cubed over 6.67 times 10 to the minus 11 times the mass of the Earth, which is 5.98 times 10 to the 24. That's a lot to put in your calculator. You should double check it a couple of times. You'll find that, then don't forget to take the square root, and you get t equals 5310 seconds, which is what I'm looking for. But we might as well change that into minutes. We divide by 60, and we get minutes, which is 88.5 minutes. That's just a sample of one type of problem. Look at these variables. I could have asked you what's the mass of the Earth based on what the satellite is doing. I could have asked you what's the distance to a satellite given certain conditions. So this is the basis of many, many problems.